Just wanted to show you a few things. The Chapter 11 is due this Friday. I think what I'm going to do is give 2 assignments. It's a long chapter, 12 is long. So I'm going to give 2 assignments. So I'll be assigning one later this week on the first maybe 5 sections of Chapter 12. And then I'll give an additional assignment. So we have had 4 assignments, and with 2 in Chapter 12, and then 1 in 13 and 1 in 14. That will be it. Chapter 13 is on covariance analysis, and Chapter 14 is on regression. Okay. I've also put the Section 4 notes up. Everything is caught up. And so we'll be talking actually about Section 3 and 4 today. But 3 is on Latin squares, and I'm not going to be spending a whole lot of time on it. It's a somewhat specialized topic. So I just wanted to point out one thing. About Section 1. Let me clear the console. So let me knit this. On a nested design, the one key thing I want you to get out of this is that AOV, the function AOV, is a wrapper for LM. It's not really a separate model, but it only actually works, I believe, for the unbalanced case. I mean the balanced case in general. LM works for all cases, including unbalanced. If you recall, based on the expected mean squares, whether or not the top effect, the treatment effect is random or fixed, you're still testing it by the secondary, the among experimental units within treatments. Because you notice, in order to get sort of the cancellation out and just be testing the alpha equals 0 and the sigma squared sub A equals 0, that we have to use that second line or the second term. And if we were testing the secondary effect, that is the sigma squared sub B equals 0, we would use the subsample, or the sample within experimental units. The problem is that LM always uses the bottom term. It always uses the one error term. It's not designed for what's called multi-level designs, or designs where you have more than one error term. And that was why the sums of square, everything here is correct, but the F values are not, because it's dividing the mean squares by this last one in all cases. So what I did here is I recomputed by dividing type by car n type. This was the example we had in test within car n type. So in this case, I've recomputed things. Now that's a little bit awkward to do that. And by the way, the other thing I want to point out is that when I'm doing contrast among types, I use car with n type for the error term. And so if you look at what I did down here, I'm using the mean square for the car, or mean square of B, whatever you want to call it. That is the second line of the table. I'm using the 1.43, not the 0.2. And so, other than that, we can proceed ahead and do multiple comparisons as we had done before. Unfortunately, that involves a bit of hand calculation. So I have been experimenting with this package LME4, and I thought it would be relatively straightforward to reproduce what you would get in JUMP. And what you get in JUMP let me so I'm going to mount the drive so we can look at this. It's a little deep. So if I look at the same data in JUMP, notice that, just to point out something about JUMP, notice that these three are justified to the left. That means they're character. What I did was, by default, they came up as numeric, but I went in and I changed it to character. So that's why I can tell their character by looking at it, even though they're 1s, 2s, and 3s. That's because I forced it to be character. On the other hand, miles per gallon is right justified, which indicates it's numeric. So if I say, fit model, which is sort of like LM, except it does give you more flexibility. Notice that the different icons, notice the continuous one for miles per gallon and the histograms, which represent the categorical variables. So if I put in type, I put in miles per gallon as Y, if I put in type here, and then I'm going to put in car, but I have to nest car within type, and so I'm going to select both and say nest. So now notice that I have type car within type. Now I don't need to put in the other term because that will be left in the residual. So I don't need to put that third term, which is test, within car and type. I don't need to do that. It's what the residual will be. But I am going to go in here and say, oh, if I go down to attributes, I'm going to say that's a random effect. Now, you have a choice of computing variance components with REML or expected mean squares. Expected mean squares is sort of the traditional, and that's what we do in the book. The REML is a residual type of maximum. The ML stands for maximum likelihood, so it's a maximum likelihood based on residuals, and it coerces it such that the sigma square estimates are not less than 0, or at least in principle. I'm going to leave it that way for a moment. Let me see how I did things over here. Yeah, I have REMO equals true here. So I had thought that it wouldn't be all that difficult to reproduce things. So for example, here are my variance components for car, fin type, and residual at 0.4 and 0.2, and that's what we had gotten before on our models. And if I look at the fixed effect, that F ratio is 22.64, and that's in fact what I had recomputed up here. But that wasn't what I originally had from the R output. Notice the 161. So JUMP does it correctly, and the variance components, which I ran these two models based upon LME4, which stands for linear mixed effects, and the 4 means using S4 classes. In other words, it's a modern version of linear mixed models. But he does it quite differently, and it turns out that it wasn't. I fit 2 models. One is I just nested car, and this is the way you specify a random effect. You put it in brackets, and then you, to the left, you sort of put where car is nested within. In this case, you would think you would put type, but in fact, that's not what you put. And so that's an incomplete model as I've specified it, but the next one is complete because I have both type and car, which will actually expand out and fit the car effect and the residual. When I did this, and actually in your homework, the one you download from the web only has one of those. I think it has a second model, not the first one. But at any rate, the ANOVA will give you the fixed effects, but you'll notice that neither of these correspond to what we got above or what Jump got. And so I plan to get together with Phil Turk, who's the real expert on mixed models, to try to resolve this. He kind of gave up on this package, the LMA4, and went back to Glimix and ProcMix and SAS. The way of expressing things here is fairly complicated. It sometimes works and sometimes doesn't. You'll notice that for this model 3, that these variance components are correct, the 0.4 and the 0.2. So they are correct, and there's a standard deviation. Now, one thing nice, if I do this, I don't actually get a separate test for the Corfin type and residual, particularly Corfin type, but I do get a confidence interval, a lower and upper, and since that actually includes 0, so you could argue that it's not significantly than 0, the variance component. Now, if you do this, I should have saved the dialogue, so I'm going to do it quickly again. It's a good idea to know how to use Jump, and SAS actually works in a similar way. So I'm back to where I was, except this time I'm going to do the traditional one just to sort of see. I'm going to keep this dialog open. And you can see that, let's see, in this case, if you do this, it actually gives type and Corfin type. It actually computes both of these. In other words, in order to get what I had above, you have to do the traditional. You didn't get that with the Rimmel. You got variance component estimates. Now, we still get variance component estimates, so the traditional way actually does correspond. The variance components are here, the same as we got, and also the F ratios are the same as I recomputed in this table. So, this kind of brings up an issue here. And the linear mixed models in this class, it's not my intent to totally resolve these issues. This is a major topic within Stat 645, linear models. Linear models actually, that course goes beyond just linear models and linear mixed models. It also goes into generalized linear models. And you can do variance components and so forth with those types of models as well. So at any rate, as I said, I've actually played around with this procedure quite a bit. And by the way, these estimates here for the type, I actually, and this is different from what you download on the corresponding section 1, if you download it, I did not put in this statement right here, options contrast equals sum. So in other words, this output right here is using a sum, but the output you'll download uses alpha 1 equals 0. So you might ask, does this, using the sum, and these are the coefficients for type, I think you can get those here. Here are the variance components. By the way, one of the nice things about, if you use the traditional way, you can get the expected mean squares. And that becomes important because back here, I've shown you how to compute expected mean squares. But this computation, and the computations we're going to do in the book, assume that we have equal sample sizes within each group, for example. And if you don't, those expected mean squares will be either slightly different or a lot different. If the n sub I, if the counts within cells are almost the same, you'll be close to this. But if the counts are quite different, then these tests may be very misleading, particularly when we get to section 4 today. So I just want to point out that these expected mean squares assume equal sample sizes. Now, as I said, JUMP will compute them even if the sample sizes are not equal, and it becomes extremely difficult. I'm going to give you some rules for computing them in general, but those rules depend upon equal sample sizes. And so that gives you a good idea, but if it's unequal, if you use a traditional method of computing things in JUMP, it actually will compute the expected mean squares for you. And that determines not only that, but it actually does what's called a synthesized f-test. Because the f-test that we've said may no longer work because of the imbalance, things may not line up quite right. And I can illustrate that later on with an example, either a two-way or three-way example, to show you that what happens if you do not have equal sample sizes. So this very much mimics what we've done using the traditional dialogue. Again, I'm talking about how we do the expected mean squares. If we do it traditionally, we get very much like what's in the book. The REML is sort of like what Doug Bates does in his LME4, but conceptually there appear to be some differences. And if you actually think you're going to resolve this by going out and search the web, you may not, because I extensively searched the web trying to resolve the differences between the way JUMP does it and or SAS and how Doug Bates does in LME4. I understand the model in Doug Bates's example. The model is fairly complex, and it's a little bit beyond what I want to do in this course. It's not beyond Stat 645, but it is beyond this course. I just wanted to point this out because if you use JUMP, you need to know the differences between JUMP and R. And SAS is similar to JUMP, but again, it uses a different constraint. It uses the last alpha equals 0. So just keep this in mind. So as I said, I've tried to use LME4 with, and the actual modeling, the actual model you use is a function within LME4. The actual model is called lemur, L-M-E-R. Lemur is the function you use to model, and the way you express your models in lemur is different than the way you do in LM. And in particular, those parenthesized expressions are the random effects, and they tell you how things are nested or crossed. But again, it's a little confusing, and so far I haven't been able to reproduce either what JUMP does or what we did above with a few modifications with the testing. So I haven't been able to actually reproduce. You would think that you would just put, you would think that you would actually just put, well, let me go back here. You would think you would just replace that one right here by type, and then that would be car within type. Not only is that not correct, you get a singularity and have a convergence. So at any rate, if Phil and I come up with some, as I said, Phil kind of gave up on this package. However, the package is widely used, but conceptually it's sort of more difficult than the way we're approaching it in this course. So we may have to just leave most of this to Stat 645, however Phil does it. So this is, I just wanted to point that out to you. By the way, I was trying to see if these coefficient estimates using the sum, I wanted to see if the parameter estimates, yeah, I think they are. The 1613, the the minus 1.3, 1.91. Yeah, these estimates right here using the sum are precisely these same estimates for type up here. So I have a certain amount of it agreeing. But notice that this model is also fitting a car with n-type, where, in other words, it's actually getting coefficients where that's not the case using the lemma function with LMA4. So again, this fit 3 is essentially what I have in your notes. So if you play around a jump, you'll see there's certain things in common. But that fixed effect test is not the same as what jump does or what we did above. So if I, over time, if I sort of figure out some resolution of this, I'll let you know. But as I said, Phil told me he had struggled with the same thing and had switched over to using proc mixed and proc clinics, which are two procedures in SAS. At some point, I may show you those just to so that you've seen an approach not only based upon R and jump, but also SAS. Do any of you use SAS at this point? It's pretty widely used. So. At any rate, now what I want to do is, we've covered randomized complete block, and we were okay there because there was a random effect. Typically the block is random and the treatment can either be fixed or random. But in both cases, you just use the error term. So there's no problem with the way R does it. There is an assumption when you do the block is that there is no block by treatment interaction. And that's a pretty stiff assumption. Sometimes you can easily justify it, but it's hard. There's a very limited way that you can test whether or not that's true. There's a test called Tukey's single degree of freedom test, but we're not going to cover that because it's a very limited type of test. Next, I want to go in and just talk briefly about the Latin square. It's a relatively short section. And I think I talked about it briefly before, but let me just go back over it. Suppose you have two sources of variability that you want to remove. You have a treatment and two sources of variability. And this originally, the reason it's called a Latin square is because it is square. You can think of it as being a square that's divided in, let's say you have 4 rows and 4 columns. Now let's say that's a piece of land in an agricultural setting, and this is where this came from. So you may have one source of ability. Let's suppose that square is on a hillside that's sloping. So as you come down, you may have a moisture. If you think about the square grid being on a hill, it's maybe also sloping one direction. As you come down the hill one way, you'll see that you may have variability because of a moisture gradient, but you may also have one the other way because, again, if it's sloping, the moisture might be going from northwest to southeast, and that would sort of cut across it diagonally. And so you want to control the variation in both directions. And so what we're going to do, if we have 4 by 4, we're going to have four levels for the rows and 4 levels for the column. We also have to have 4 treatments because we're going to randomize the treatments within that Latin square so that each treatment appears exactly once in each row and column. Okay. And there's software that allows you to choose all possibilities where that could occur, and then you choose one at random. Now, the point is we're going to have a treatment effect, and we're going to have a beta and gamma effect. The beta and gamma effects are the sources of variation you're trying to control. I'm not particularly interested in the beta and gamma. I'm simply trying to remove error variability. Well, how many experimental units do I have altogether? Well, if A represents, in what I was talking about, 4, if it's A by A treatments, okay, but it's still only, the number of plots is still only A squared, so there are A squared observations. So the total will have A squared minus 1, the treatment will have a minus 1, and all of these will have a minus 1. And you can then calculate what's left in the residual is a minus 1 times a minus 2. So the residual can get quite small. If you start out with a as 4, then each of the effects has 3 degrees of freedom, and the bottom one has, it will be 4 minus 1, which is 3, and then 4 minus 2, which is 2. So there are only 6 degrees of freedom. And this is one of the problems with this design, is that you remove variability, hopefully, from that error term. But if you don't, you have a problem because you only have relatively few degrees of freedom, and therefore you may not have much power. The book shows you how to calculate it by hand, and here I've shown you the calculations also. Well, maybe not all of them. Well, actually all of them up here, if you use the computing formula. And again, we're just looking at the deviations from each effect from the grand mean and squaring those up. And this is the computational formula. So, so at any rate, we're going to test everything again by the error term. I don't have the expected mean squares here, but the expected mean squares, everything is tested by the bottom residual term. And so here we have an audio score of 3 subclasses, 3 orders, and 3 devices. And I'm most interested in the devices, of course. So if I have the devices and I have the noise, you can see there appears to be a pretty big difference. And if we do the analysis of variance, we can see that we have subject, order, and device. We can see that everything is significant. Well, the order and device is, but not the subject. Okay. So, and again, we could do multiple comparisons here using the error term to see which devices are different from each other. Again, we could do that. So the Latin square, the reason we do it is to control 2 sources of variability. Remember, we have a completely randomized design. That's where you simply randomize the experimental units of the treatment. We control no sources of variability there. And if there's a lot of noise in the error term, then it's hard to find differences. The next step was to say, okay, let's control 1 source of variability. What was that design called? Does anyone remember? That was section 2. That's a randomized complete block. Now I say block, and again you can think in an agricultural sense, but it's much more general than that. So you're controlling 1 source of variation with the randomized complete block. We pay it at the price of not being able to break out the error term, or the interaction term. If there is an interaction term, it's confounded with the error. As I said, usually you have some knowledge about whether there's really an interaction term. And then finally, if you want to remove 2 sources of variability, then we use the Latin square. But again, the Latin square has a couple drawbacks. And by the way, the 2 sources of variability are almost always considered random, and the treatment could either be fixed or random. A lot of times, though, in that case, in Latin squares, it is fixed. So, so at this point, we're ready to move on to factorials. And factorials are sort of a big topic. And in 513, you'll delve into factorials in more depth. And in particular, in this book, we talked about nested effects. And we'll now talk about crossed effects. So there's some concepts that you ought to be learning. The first 3 sections are more in the realm of what we call experimental design. And experimental design, you're trying to control variation, or at least account for the sources of variation. Okay. Now the nested is sort of, I mean, you're breaking out the subsampling from the main experimental unit, and it's not quite an experimental design as the way block designs are, or Latin square designs, where you're really trying to control variation, because they're the nested design we looked at is like a completely randomized design, except we subsampled experimental units. So we could call it an experimental design because we're studying the variation, but it's not quite the experimental designs in 2 and 3 which control the variability. But at least it gives us some sense, the nested design, of the sources of variation. Now the factorial design extends the one-way analysis of variance such that you have, initially in this next section, we're going to have 2 factors. We'll call them A and B. And the difference between a factorial design is that every level of A appears at every level of B, at least once. Now that's not quite true, but because there are a class of designs called fractional factorials, which are common in industry, and that's when you don't have a lot of experimental units. And so we make it in such a way, well, when you have A by B, you not only have the A effect and the B effect, but you have what's called the interaction between A and B effect. And what we do in a fractional factorial is we partially confound the interaction. And we do that because we often cannot have enough samples because of the cost of getting the samples. This fractional factorial is not something we're going to cover in this course. It's covered rather extensively in 513 if you take it. But that's particularly important in industrial experiments where you often cannot go out and collect lots and lots of data. Okay, so let me close this, and let me bring in, let me go to section 4. And I'll set the working directory to that. And let me knit this, and then I'll show you what the model is. Okay. So this is the 2-way, or A by B factorial. And the reason I call it A by B is because if we look at our model, if we look at the model, we have mu sub ijk equals mu plus alpha sub I plus beta sub j plus alpha beta ij plus epsilon sub ijk. And I goes from 1 to A, j goes from 1 to B, and k goes from 1 to n. Now, in general, k could go from 1 to n sub ij. In other words, if you think of it as a matrix where you have cells, and if A is on the rows, it would go row 1, 2 down to A, and in the columns would be 1, 2 up to B, and it forms a grid. And so we have levels of A. Level 1 of A with level 1 of B would be in the top left corner in that particular cell, in the 1, 1 position. And in that case, I would equal 1 and j would equal 1. Now, if I equals 1 and j equals 2, where are we? We're in the 1, 2 cell, meaning we're in the first row, second column. Is that clear? And so we have, in each of those cells, we have observations. And we're assuming we have n observation where n is greater than 1. And we're assuming they're all equal. So you could think of your data being in each of these A by B cells. So I have A rows, B columns, so I have A times B cells. And so you could think of your data filling up those cells. Does that make sense? And there are n observations in each cell. Now keep in mind, here's a couple things that could happen. if it's an observational study, the n sub ij will not all be equal if it's observational as opposed to designed. We would try to design it such that we have equal sample sizes in each cell. And in fact, we might do a preliminary power calculation so that we know how to choose n. Now that gets a little more difficult. Usually when you're computing power, you do it for a simple two-way t-test, or you do it maybe for a one-way analysis of variance. But it becomes more difficult to compute this for this two-way. However, let's suppose for the sake of argument we have a 3 by 4 factorial, meaning 3 levels of A, 4 levels of B. How many cells are there altogether? There are 12, right? 3 times 4. There are 12 cells. And so I could just stretch those out, those 12 cells, as if it's a single factor. And I could actually compute power that way. But it's a little misleading because if I do that, I can't account for interaction. But it's going to be hard to account for interaction anyway when I'm computing power. But I could kind of stretch it out and compute power that way. Now, so we could have unequal n. And unequal n affects the expected mean squares. But there's something a little bit more insidious that could happen. Some of the n sub ij could be 0. That's called a missing cell. This creates difficulties in your analysis if any of the n sub ij's are 0. If too many of them are 0, then you have a real problem. In fact, if you talk about a connected factorial, you could always get from any cell to any other cell going through cells that have observations. And I mean going either horizontally or vertically, not diagonally. So if I had 2 cells like this and these 2 are missing, I can't get to the second cell without going diagonally. If you have a design like that, it's called disconnected. And in those kinds of cases, the analysis, it's almost as if you have 2 sub-experiments that are disconnected. If I had a group of cells here and a group of cells here and nothing here, then it's like 2 separate experiments. So that's a really bad, you might as well not put them together because you can't make inferences. But sometimes they're partially connected, but you have some missing cells. And again, if you have 1 or 2, you can kind of adjust for it. And there are ways you can do imputation to try to adjust for it, but this is just a problem that does occur occasionally, particularly if it's an observational study. And if it's an observational study, you may have extreme unbalance, so these expected mean squares we're going to compute aren't even going to be remotely accurate. Okay. So this is our model. Alpha sub I represents the rho effect as I described it. It's the factor A effect. The beta sub j is the factor B effect. And what is the AB? Well, that's the interaction between the two. Let me just give you a preview of this. This is what's called an interaction plot right here. If there is no interactions, segment-wise, I'm plotting the method here. I'm plotting like A here, the outcome variable here, and the other factor here. So here's one factor, and so each of these lines represents the levels of one of the factors, and this represents the levels of the other. If these 4 lines were more or less parallel on this side, and these 4 lines were more or less parallel, then we would say we have no interaction. If the alpha sub ij is in factor all 0, then they're exactly parallel. Now we have random variables, so they're never going to exactly be parallel in practice. But notice that on the right-hand side, those 4 lines are reasonably parallel, which indicates that's okay. And on the left-hand side, notice that 3 of the 4 are, in fact, more or less parallel, but 1 is not. And so the interaction here is being caused by field 2. Field 2 has and this is oil output, field 2 using carbon dioxide, and I'm not sure how this is used as a way of extracting oil. It's mechanical fracking and so forth. So field 2, using carbon dioxide, is much lower than you would expect, and that's what's causing the interaction here. Now, the interaction can be much more extreme than this, but that just gives you a preview of what I'm talking about. So if the alpha sub I, if the alpha beta, and that doesn't mean alpha times beta. That's sort of like one symbol, alpha beta. But it has two subsets, ij, and that's the interaction between factor A and factor B. If there was no interaction, I would simply have an additive model, the effect due the alpha sub I plus the beta j. That's called an additive model. We would just have an additive effect. It is not just an additive effect if there's an interaction. There's some other term added, and it depends on the I and j. So that messes up our nice additive model if we have this interaction. Of course, interactions are pretty common. Sometimes we talk about them as synergistic effects. You take this and this together, and it's more than the sum of the two. Of course, it can be the reverse. You can take two drugs together, and they'll kill you. That's an interaction. Together, individually, they may be okay, but you put them together, it may be fatal. That's an interaction. Okay, so this is the gist of the model we're going to be looking at. So I define these here. Now, here's the kicker, though. Either the A effect or the B effect can be random. In other words, I could have three different models. I could have both A and B as fixed, A and B as random. Or I could have what's called a mixed model, where A is fixed and B is random, or vice versa. The mixed models is where we start to get complicated. So let's talk about the fixed effects model first. The fixed effect model is the situation where both A and B are fixed. And in this case, the expected mean squares are quite easy to work out. We notice that it's sigma squared times NB times some quadratic in the alphas. For the B effect, it's being cut off here. I've got to adjust this thing. At any rate, it's slightly off, both vertically and horizontally. The B effect, again, is n times A. Notice that the first one is n times B. I'm going to show you how to get these expected mean squares. We're going to have a rule that gets all of these when we get to the next section. N times A for the B effect times the quadratic in the betas. And then for the interaction, it's sigma squared times n, and then there's an alpha beta squared effect, quadratic in the alpha betas. Now notice that interaction term does not appear in either the A or the B. So all three of those are tested by what? The residual. I didn't write that down there, but the residual has an expected mean squared of sigma squared. So the mean squared for A over the mean squared residual tests the alpha sub I as 0. The mean squared for B over the mean squared for error tests the betas as 0. Because notice that if the alpha is 0, then the expected mean squared reduces to sigma squared, which is the same as the residual mean square of sigma squared. So I'd expect the f-test to be about a ratio of about 1. And so, and again, the interaction is tested by the residual also, the mean square for AB over the residual. So I can do these three tests, and so that's all pretty simple. Now what about if we have a random effects model? Now notice here, when we compute this, all of them, but the random effects, have the interaction term in them. So in other words, the sigma squared plus n times sigma squared sub AB plus, again, since they're both random, it will be some function of sigma squared sub A. And the second one has the interaction term plus a function of sigma squared sub B. And then the A by B is sigma squared plus n times sigma squared sub AB. And then there's the The row I didn't write is for the residual, or the error, and it just has an expected mean square of sigma squared. So what test here? Well, both of these now are tested by the interaction, right? So if you have a random effects model, then we are using the interaction to test both of the main effects. Now, there's another point that you should realize is that, well, you know, it gets difficult to interpret the main effects if, in fact, there's an interaction, because then you tend to focus on that interaction graph, or what is the interaction. So, so we test everything by the interaction, and notice that the degrees of freedom for the interaction is a minus b times a minus 1 times b minus 1. So if a and b are not very big, you have very few degrees of freedom. Now, these are all important to consider when you're looking at this, because if a is, say it's a 3 by 3, then that means what? The degrees of freedom, do I not have that written down any place? I should add that. But the degrees of freedom will be a minus 1 for a and b minus 1 for b, and a minus 1 times b minus 1 for the interaction. So therefore, the degrees of freedom of a minus 1 times b minus 1, if it's a 3 by 3, it will be 4 degrees of freedom, which isn't all that much. So keep that in mind if you have a fully random effects model. Okay, now, is everyone clear on that? We've been talking about random effects before. Here I'm talking about it in just a factorial. Now, I want to mention that you can embed these factorials in like a randomized complete block design. In other words, I had a treatment and I had a block effect. That treatment could be replaced by a factorial. So you can embed a factorial design in a block design. Therefore, I make a distinction. In fact, I make statistically 3 distinctions that you need to be aware of when you're working on designing an experiment. And they're not unrelated. One is the experimental design. And I'm going to define that to mean controlling variability. How do you control the variability? The next one is treatment design. What is the relationship of the treatments to each other? Are they nested or are they crossed? If they're crossed, they're a factorial. If they're nested, they're a nested type design. There's a third one you have to be aware of, and that's the sampling design. The sampling design deals with power and how many experimental units I have. So if you're designing an experiment, you ought to be thinking about all 3 of those: the experimental design, the treatment design, and the sampling design. The experimental design can help you out with power. So if it's too expensive to get much data, then you better try to control variation, because if you want high power, you have a couple choices. You either reduce the error variability or you increase the sample size. Those are your main choices. So if I reduce the variability, I might get by with fewer observations. But if I can't reduce the variability, then in order to get decent power, I'm going to have to increase the sample size. So these are not unrelated topics. The treatment design gives you a form of implicit replication, and we'll talk about that later. But now we get into, I'm going to talk about mixed effects. And notice I say mixed effects standard model. Well, why do they call it a standard model? That's because there is another model that we'll call the alternate model. Now, so you need to know the difference, because JMP uses the alternate model. So let's take a look at the standard model. A fixed and B random. Of course, it could be the reverse. It could be B fixed and A random. And you just flip things here if that's the case. So if A is fixed, so we have alpha sub I is for A, but sigma squared is for B. Under the standard model, the expected mean squared for A is is sigma squared plus this AB term plus the quadratic in the alphas. The B term is sigma squared. It's an expression in terms of sigma squared sub A, but there's no interaction term there. And then for the AB, there's just the AB term. So therefore, the A effect is tested by what? The A effect is tested by the interaction. The B effect is tested by the error term. And because the error term has an expected mean squared, just sigma squared, and the interaction is just tested by the error term. So the random effects are tested by the error term, but the fixed effects is tested by the interaction term. Now, what is the standard model? The standard model is what? How do we assume the alpha beta is distributed? In the standard model, what we do is what's called a finite correction based on finite sampling. So, and if you compare this to the alternate model, which I think it says the alternate model is the alpha beta ij or uncorrelative common variance sigma squared sub AB. Well, what happens here is we have a slight covariance, depends upon 1 over A, and we also have an adjustment to the sigma squared sub B. And so in this case, there's slightly different assumptions. Now, which ones are more realistic? The alternate model, I would say, is making more assumptions than the standard model. But when you write software, now in principle in R, we could do it any way we want. But when we write software, we have to make a choice. And Jump made the choice to use the alternate model. I need to actually check SAS what they use, but I suspect they use the alternate model and Jump does, but I need to check that. So, what's the difference? If I look at up here for the, if I look here for the standard model and here for the alternate model, what is the difference? There's only one. But look at the B term. What's its expected mean squared? Notice that both the fixed and the random effect both have the interaction term and the expected mean squared. So both of those are tested by the interaction. So both are tested by the interaction in the alternate model, whereas in the standard model, only the A effect is tested. So, so we need to be careful, you know, when we look at this in terms of which, you know, what are we doing? We need to be aware of what we're doing. And most people are not. They just run Jump and that's it. That's my interpretation. Not realizing that there's a somewhat different way of doing it. Of course, you could recompute it in Jump, just like you can recompute it in R. So, are there any questions on that? Again, what I said is that we will learn, I think we're going to learn how to compute expected mean squares using the standard model in this book. You may not realize it, but there are a number of controversies in statistics. This is one of them. The big one is sort of a Bayesian versus a frequencies interpretation of probability. That's the biggest one. This may also affect how you estimate your variance components. Up here, if I'm getting the variance component for B, I simply take the mean square for b over the minus the mean square residual and divide by n times a. Whereas down here, I'm going to take the mean square for b minus the mean square for a and divide it by n times a. So when I compute the variance components, they're different for the two models to get things to cancel out. Does that make sense? So it not only affects how we test, particularly how we test the fixed effect, but it also affects how we estimate the variance components. Okay, to finish this up, although I'm going to, if I have time, I'm going to show you jump. We have oil in barrels we're measuring. We're measuring the quantity of an oils that are produced using 3 different methods of extraction and 4 different fields. Now, if you were thinking about this, what's fixed and what's random here? Are the methods fixed or random? They're probably fixed. You have 3 methods. But fields, on the other hand, you can have a lot of oil fields. So you're going to select 4 at random. So fields is probably random and method is fixed. Is that clear from the context of the problem why that would be the case? Now, it could be that you're just interested in those 4 fields. It could be, but not likely. So we're going to read the data in, and we're going to make both method and field a factor. And then we're going to fit the model, barrels tilde field, a method plus field plus. Notice that, I think I've talked about this before, but the interaction in R is method colon field. Okay, so method plus field plus method colon field. So that fits the model. And we'll get an AOV. And what do you think? What do you think is going to be the error term? Those F values, how are they computed? Well, they're all computed by the residual, right? Now, if we were going to do the standard model right here, we would use the AB interaction to test the fixed effect. The interaction to test a fixed effect. So I guess, let's see. Yeah, the fixed effect is method. So I would use the method by field. So I would divide 44 divided by 3.5. That's what I've done here. This is rounded off. This is unrounded. So the actual F test for method is 12.63. Now, if you were doing the alternate model, in order to test field, you would also divide the mean square of 3.3 divided by 3.5 as opposed to the residual. Now that kind of makes a difference here, doesn't it? Because under the standard method, there's significant field-to-field variability, right? In other words, that 4.37, this F value right here for field, for the random effect, again, if I go up and look at the random effect, here, the random effect is tested by the error term. So this is the correct test using the standard model. But if I were using the alternate model, I would be dividing it by the residual mean squares for the interaction. That would be 3.3 divided by 3.5. That's an F of less than 1, and therefore it would not be significant. So here we see a difference between a significant result using the standard model and a non-significant result using alternate model. At any rate, if you're mainly interested in field, that test is the same. And so we do seem to have a strong field effect, but we also have what? We also have an interaction effect. So the interaction effect, the p-value is 0.011, so we have a significant interaction effect. And we also, under either method, we have a significant method effect. So notice the residual variation is 0.8, And if I wanted the interaction variation, I would say the 3.5 minus 0.8 divided by n. And what is n? I forget what n is. But at any rate, okay. So there is a difference. Now, since we have an interaction, you're almost always going to want to do what's called an interaction.plot with method and field with barrels. And that just plots the mean. Now, again, technically, this is just using the means. One of the things that someone in my next class says, I've never heard of least squares means. Well, you should, because the least squares means are the same as the model means. When you estimate the parameters, the alphas, the betas, the mu's, and so forth, and you get predicted values. So if I wanted those, let's take, remember I said we have A rows and B columns, right? And we have observations in each cell. Well, the sample means, or the cell means, are simply the averages within each cell. Now you might think that if I take, if I get mu plus alpha 1 hat plus beta 1 hat plus alpha beta 1 1 hat, that is the cell mean for 1 1. And you might think that if I take mu hat plus alpha hat 1 plus beta hat 1 plus alpha beta 1 1 hat, that you would get the same thing as the cell means. And you do if it's balanced. But you don't if it's not balanced. So the model means, or also called the least squares mean, are computed from the model. And they are, if we fit a model, then we should use the model to estimate stuff. And so we use the model means or the least squares means, not the cell means. The cell means doesn't know anything about interaction, for example. I plotted the same thing twice. And in both cases, if I look at field 2, if you look at this line, if you would take that point for field 2 and bring it up here, again, you'd sort of see that you have parallel segments. So by segments, here I have 3 segments. I have this first segment here. I have the second segment here and the third segment here. What we're saying when we say no interaction is when we do an interaction plot, that within each segment, we expect change from segment to segment. But if we don't have an interaction, then those segment lines should be more or less parallel. They won't be parallel because of random variation, but they shouldn't be way off. But again, we can see that field 2, whichever way you look at it, whether you look at field as along the x-axis or method along the x-axis, and then you flip what's in the legend, you're plotting the same, 12 points? This is a 3 by 4. So you're plotting the same 12 points. Now this is, the interaction plot is only plotting the cell means though, not the model means. So if you wanted to plot an interaction plot with the model means, they may be slightly different than this. But again, I'm simply using field and method and barrels. I'm not using a model to get that interaction plot. So be aware that those are the cell means that I'm plotting. And they'll give an indication of the interaction, but again, they're not the same as the model means. Okay, are there any questions on this? Well, let me just quickly go in and look at section 4, and I'm going to look at the oil. I have looked at this in SAS, but we'll come back to this. So we have the 3 methods here and the 4 fields. And so if I'm going to fit this, I'm going to fit model again. Barrels will be Y. And let's put method here. And we'll put field. And then we're going to put method. I'm going to select both and put crossed. Now field is going to be random. And the interaction, if an interaction contains a random term, it's random. So it's also random. And I'm going to do the traditional method. And so let's keep this dialog open and let's look at it. So when we do the analysis of variance, let's see. You see, these terms are those coefficients, right? The 8, the 6, the 2, and 2. Those are the coefficients, the NAs and the NBs and the Ms. And so what does that say? Notice the 222 says that method, field, they all have that 2. So that's saying that method and field are going to be tested by this interaction term, which is the alternate model. And so here is my test. And so here we get our results. And if I go back, notice that method has a 12.6. Let's see if that's the same as, yeah, that's the 12.6 that I had to recompute because R didn't compute it correctly. So these are the tests using the alternate model. Now, what we get for field, which is an F ratio, remember I said it wouldn't be significant because it was slightly less than 1. And you can see it's 0.94, it's slightly less than 1, using the alternate model. But it was significant using the standard model. So just so you understand this, so this is telling you what's tested with what. Now this, what's called the test anomalous synthesis. The reason that's important is because if you have an unbalanced design, you don't get these nice coefficients here. And what you try to do is synthesize a correct term in the bottom to do your testing. But you don't get these nice 6s and 2s if you have unbalanced designs. In other words, if it's unbalanced, instead of getting a 222, you get something different than that. So using the method by the interaction wouldn't be quite right. And you could try to combine mean squares, or actually sums of squares, to get a correct error term. And sometimes you can do that, and sometimes you can't. And later on, I'll show you an example of that. At any rate, this is the way JMP does it. So I presented both the standard. Most books only present one. But unfortunately, since there's different computer software out there, you should know the distinction and know what you're doing. Which is better? Well, as I said, you're making more assumptions with the alternate model. But JMP uses it as long as you know that you're assuming no covariances. You're not assuming, what they're not assuming is finite sampling. Whereas the standard model assumes you have finite sampling. What's called a finite sampling correction factor. So if you had a huge number of fields and you sampled 4, then that covariance is probably very small. But if you have a finite number and you're sampling out of that, then in fact the standard model may be better. It's unfortunate that it has such an effect on both testing and the variance components, but it does. It changes the variance component estimates for the random effects, and it changes the actual test you carry out. So this is kind of an introduction. Next time we're going to look at the A by B by C, and when we do that, we're going to learn how to compute expected mean squares, not sort of using statistics. For those of you who may know, computing expected mean squares for a random variable, in this case, you can do it. It becomes rather tedious to do it. We're going to have rules that show you how to compute it in the balanced case. Okay, any questions? Okay.